Okay, so the first question they've given us is, or what we're going to look at is probability. And they want the probability of drawing from a normal deck. So a normal deck has 52 cards, of drawing a diamond or a 6. So the first thing we want to define is how many diamonds are in a deck and how many number 6s are in a deck. Okay? And we're only drawing one single card. So we're only drawing out of this once. So the first thing we have to figure out is how many diamonds are in a deck. Do you know how many diamonds are in a deck offhand?
13.
13, that's right. That's good. And essentially, how else could we figure that out? How many different types of cards are there? You have your diamonds.
The hearts, spades, and clubs.
Yeah, so essentially this is a quarter of a deck of cards. So we can divide this value by 4, right? And we get our 13. The other idea is 6. How many 6s are in a deck?
4.
4, that's right. We have 4 6s in a deck. Okay. So when drawing, now the only thing is there is a bit of a union between these. This card here, there is a possibility of getting a 6 of diamonds. So there's repetition between that one card. Okay. So we actually end up double counting if we were to add these strictly. If we were to just strictly add diamonds and value of 6, well, that would be 17 total cards. But what actually ends up happening is one of these 6s is a diamond. So we don't want to double count that. So if we've counted all the diamonds, that actually takes away one of our 6s. It really is only 3 more cards on top of those diamonds. Okay, so really this is looking at 13 and 3 in this case when we're looking for OR. So we have the 13 diamonds, which includes the 6 of diamonds. Okay, so we have all 13 diamonds, and then we have 3 more diamonds, which means we have the 6 of hearts, or sorry, not diamonds, but 6s. We have the 6 of hearts, we have the 6 of spades, looks something like that, and we have the 6 of clubs. Okay, we don't double count that 6 of diamonds when doing this. So that's a total of 16 cards. So when we're looking at 16 of 52 in this case, if we were to reduce this, and we divide the top number by 4, so they probably always want us to reduce our fractions to the smallest number possible. So if we reduce 16 by 4, that gives us a value of 4. And we already talked about it. We'll do it on a calculator just to prove it. 52 divided by 4. 52 divided by 4 gives us our 13. So we end up with 4 out of 13. So the probability of drawing a diamond or a 6, is that what they got? Yeah. They got 4 out of 13. So that's our probability for this question. Does that first one make sense?
Yeah.
Just to recap this idea here where we double counted a number, it can be represented in a Venn diagram. We put 2 Venn diagrams. We have diamonds, which is, there are 13 altogether, and 6s, well, there's 4 altogether. And there was one card that overlapped, which is our 6 of diamonds, right? So because of that overlapping, what you can do is you can take these values and subtract the number in the middle, whatever that disjointed is. So in this case, that'd be 13 plus 4, subtract 1. Well, we know 13 plus 4 is our 17. And because one card is double counted, we subtract by that value, which essentially takes us to the 16. The hardest part about this question was figuring out how many cards we're trying to draw. Okay. There's another question. So next question asks us, a card is drawn randomly from a deck and then replaced. Okay, so we draw once, so we'll call it draw number 1. And then it says the second card is then drawn, so draw number 2. So we kind of split the 2 of them up. Determine the probability that the first card is a spade. So in draw 1, we're looking for a spade. And in draw number 2, we're looking for the jack of clubs, so very specific card. Okay, I'll do my best to make that simple. Now what they told us is in our first draw, and we know again it's a normal deck, so we're out of 52. But they told us in between the cards are replaced. Okay, and that's actually really important. What that means for us is in both of the draws, we're going to be out of 52. Okay, so it's very possible, well sorry, I shouldn't say very possible, it is possible to draw the same card twice because it's replaced. So say I take the ace of hearts the first time, okay, and then I replace it. Well, in draw number 2, because it's replaced, it's possible I take the ace of hearts again. Okay, that replace is very important. Had it not been replaced, then we're no longer drawing from 52 cards. How many cards would we be drawing from?
51.
Yeah, exactly. And that's exactly, I think, where you made your error in this question here.
Yep.
Okay, so spades, how many spades are in a deck?
13.
Yeah, 13. So that gives us a 13 out of 52 chance, right? And then how many jack of clubs are in a deck?
1.
1, that's it. So this is the probability of draw 1, and this is the probability of draw 2. And when calculating our probabilities here, determine the probability that the first card is this, and then the second one. So because it's very specific, we're multiplying the two of them. We're taking the idea of getting these exact ideas. So in the first one, I draw a spade, and then in the next one, I draw a very specific number. Well, we have to multiply the two of them. And the two of them together, do you recall multiplying fractions? 13 by 1 will give us our 13, okay? And 52 by 52 is going to be a very large number. 52 squared, 2,000. And I think we can actually divide that by 13. So let's see. 208. So we can reduce this fraction. It's an awkward looking fraction. We can actually divide the numerator and the denominator by 13. And when we do that, 13 divided by 13 gives us a value of 1. And 2,704 divided by 13 is 208. So the probability, and it makes sense, of drawing a spade and then drawing a very specific number is pretty rare. 1 in 208. So you have like a 0.05% chance of actually doing this. It's pretty tough to do something like that with cards.